Every morning, many of us check the weather forecast, right?
Yeah.
Or plan a commute, maybe even book travel way in advance.
hmm
We kind of operate assuming things are, well, predictable.
Comfortable assumptions.
Exactly. But what if fundamentally a lot of the natural world just isn't? Not just hard to predict, but inherently impossible to forecast sometimes.
That's precisely it. And that's what this deep dive is all about. We're looking at classical chaos theory, the famous butterfly effect, and what it really means for predicting, well, anything.
Yeah.
Storms, asteroid paths, you name it.
And our sources for this, they really bring together some fascinating stuff. Maths, physics, real events, even philosophy about what we can actually know.
Yeah, quite a mix.
So our mission here is basically to unpack these core ideas. We'll walk through the surprising history and show why some things just seem to be beyond prediction. We want to give you a shortcut to understanding this complex-sounding topic.
Because it really does apply more widely than you might think.
Okay, so let's start with that butterfly effect. Most people probably connect it with, I don't know, maybe a movie plot.
Right, a dramatic chain reaction. But its origins are actually in serious science, which is what's really interesting.
Yeah, and that link between the popular idea and the actual math is key, isn't it? The butterfly effect is sort of central to chaos theory,
It is.
suggesting that a tiny, tiny change, the classic example being a butterfly flapping its wings in Brazil,
Right, the famous title.
could eventually cause a huge difference, like a tornado in Texas.
It's a vivid metaphor, yeah, but it captures this extreme sensitivity some systems have.
And Edward Lorenz, who was really a pioneer here, he formalized this. His talk, "Does the flap of a butterfly wing in Brazil set off a tornado in Texas?"
Hmm.
It wasn't just rhetoric.
No.
It underlined this unpredictable, nonlinear nature, small changes having these massive disproportionate effects, not simple cause and effect.
So how do you actually show that? Mathematically, I mean, beyond the metaphor. How do you sort of visualize this chaos? Well, one powerful way is through simulation. Imagine you have three particles, three little balls maybe,
Okay.
and they start from positions that are almost identical, so close you can't see the difference initially.
Right.
But then you let time run, and very quickly, their paths diverge wildly. They end up in completely different places.
Ah, okay.
And seeing that visually, it really hammers home how those tiny starting differences blow up. It mirrors that butterfly idea perfectly.
Wow. And that idea, it stretches beyond physics too, doesn't it? It makes you think about like small choices in your own life.
Absolutely.
A tiny yes or no decision years ago could lead you somewhere totally different now. It's pretty profound when you think about it that way.
It really is. And speaking of origins, it's interesting how they first stumbled onto this. It was almost by accident, wasn't it, in meteorology?
Yeah, Lorenz and his collaborators, Ellen Feder and Margaret Hamilton, were crucial in helping quantify it, right?
That's right. They noticed these tiny rounding differences in their early weather computer models.
Just tiny numerical changes.
Yeah, minuscule. But they led to completely different long-term weather forecasts. Massive, unpredictable changes.
So if that sensitivity is really fundamental, what does that tell us about trying to predict the weather accurately, say, beyond a week or so? Is that just a tech problem we'll solve, or is it a hard limit?
Well, that difficulty, predicting accurately beyond maybe 7–10 days, it seems to be a direct result of this sensitivity. Chaotic systems like the atmosphere, they just inherently resist precise long-term prediction. It's not just about better computers or more data, necessarily. It seems to be baked into the system itself.
But chaos theory isn't just about the weather, right? The insights apply elsewhere. The source material mentions things like asteroid tracking. There was anxiety about one called Y4, and even a satellite coming down.
Exactly. And it raises that question. Why the uncertainty if we're generally good at predicting orbits?
Yeah.
It's the same principle. Tiny errors in measuring an asteroid's initial position or speed get magnified over time.
So a tiny error could mean the difference between a near miss and...
Yeah, and a potential impact.
Yeah.
Which understandably causes public concern until they get more observations to narrow down the possibilities.
Okay, so a lot of this unpredictability we see comes from imperfect starting information. But is there any way to manage this? Is there some math that helps bring some order to the chaos?
Well, there is something called CAM theory, Kolmogorov-Arnold-Moser theory.
Okay.
It's a mathematical framework that helps look at the stability in these complex dynamic systems that change over time.
Like orbits or weather.
Precisely. Think of it like this. Even within a generally chaotic system, CAM theory can help find sort of islands of stability.
islands.
Yeah, regions or conditions where behavior is more predictable, more stable, even if the overall system is chaotic. It tells us maybe not the exact outcome, but the odds of certain things happening. It gives a kind of probabilistic handle on
A
things.
bit of comfort amidst the chaos.
You could say that, yeah.
But the material we looked at goes even deeper, right, into the philosophy of it all. Is unpredictability always just about missing data?
Not necessarily. Sometimes, yes, it's the butterfly effect, sensitive dependence on initial conditions we don't know perfectly.
Right.
But other times, the problem seems to be more fundamental, logical almost. These are called undecidable events.
Undecidable, meaning what?
Meaning situations where no amount of data, no matter how perfect, can actually give you a definitive yes or no answer. It's not just about practical limits of measurement.
It's like the question itself doesn't have a computable answer.
Something like that. It suggests there might be fundamental limits to what can be known or computed, period, regardless of technology. It
Yeah.
really challenges the idea that every question has a discoverable answer.
That's a huge thought, that some things are just unknowable.
Mm-hmm.
And then the research even asks this wild question. Could nature's unpredictability, like in fluids, lava, tsunamis, could that actually be harnessed? Like, could a fluid compute something?
Yeah, that's a fascinating, really cutting-edge idea. Visionary thinkers like Roger Penrose and Terence Tao have explored this.
Wow.
Could the incredibly complex, unpredictable way fluids move actually be performing some kind of computation? It pushes the boundary of what we even mean by computation.
And the complexity of fluids links to another big challenge, right? The Navier-Stokes equation.
Yes, absolutely. These equations are fundamental for modeling how fluids move: water, air, anything that flows. Engineers, scientists, they use them constantly.
But even with something so basic, so fundamental as fluid flow, there are still deep unknowns.
Big time. A central mathematical puzzle remains unsolved. We actually don't know for sure if these equations always have smooth, well-behaved solutions for all time.
What's the alternative?
The alternative is that they might blow up, meaning mathematically at some point in time, properties like the fluid's speed could theoretically become infinite.
Which doesn't happen in reality, obviously.
Right. Water doesn't suddenly move infinitely fast. But the math allows for this possibility, and proving whether it can or cannot happen is one of the biggest open questions in mathematics. The Millennium Prize problems, even.
So even how water flows holds these deep mysteries.
It underscores how much we still don't fully grasp about fundamental natural processes.
So wrapping this all up, what's the big takeaway for listeners from this deep dive? It feels quite humbling.
I think humbling is the right word. This whole exploration really points to inherent limits. Limits on our ability to predict and maybe even control natural systems.
Yeah.
Whether it's because of classical chaos or these deeper issues of undecidability, there are frontiers that seem genuinely out of reach. It's humbling for science, for philosophy,
Yeah.
really for all of us.
Okay, so let's recap the key points from our sources then. First, classical chaos. Tiny changes, huge unpredictable results. That's the butterfly effect in action.
Right. Extreme sensitivity.
And second, this chaos theory explains why perfect long-range forecasts for things like weather or even tracking asteroids precisely are so difficult, maybe impossible, despite our tech.
It's often a fundamental limit, not just a technological one.
And third, sometimes the limits aren't just about missing data. These undecidable events suggest some things might be fundamentally unknowable or uncomputable.
A deeper kind of limit to knowledge itself.
And finally, those big unsolved questions remain, like the Navier-Stokes equations for fluids, can they blow up? It shows we're still figuring out the basics.
And taken together, chaos and undecidability really call for a kind of intellectual humility, accepting the limits of our knowledge and control.
Which leaves us with a final thought for you, the listener, something to chew on. If a butterfly's wing can, theoretically, change the path of a storm, what seemingly tiny choices or circumstances, or maybe even random events in your own life, might be setting your future on a vastly different course? Thinking about these limits, this inherent unpredictability, and maybe it changes how you approach planning or risk or even just day-to-day decisions.
It certainly makes you appreciate the complexity.
It does. It's humbling, yes, but it also offers this, I think, profound appreciation for the incredibly intricate, unpredictable dance of the universe we're all part of.